the tutorial sheet itself, because these are the questions that we're going to solve, your questions from your tutorial sheet. But before we solve these questions, what are some of the basics that you are supposed to understand on this topic? You must understand that the chemical bonding is just a coming together of two or more atoms together. Let me say I've got, this is one atom and this is another atom. When they combine, they are going to give us one atom. This is a chemical bond that has been formed. So this is the basic premise about chemical bonding. Now basically there are two main types of chemical bonding that you should understand. Number one is what is called ionic bonding. Now then number two is what we call non-ionic. So what's the difference between the two? Now in ionic bonding, you are dealing, it's a bonding between a metal mostly and a non-metal. Okay, so metals themselves, they tend to lose electrons. On the other hand, non-metals, they gain electrons. Therefore, this kind of bonding, it usually involves the transfer of electrons, and this is very important as far as this topic is concerned. Then on the other hand, we've got what we call non-ionic bonding. Now non-ionic bonding, it also has different types. One of the types is covalent bonding. Now this is the one that you're mostly supposed to focus on. Things like coordinate bonding, they barely bring those. Okay, so mostly it's about chemical bonding. Now mostly it's about covalent bonding. Now covalent bonding deals with the sharing of electrons, mostly occurs between non-metals. Now there are about two types of covalent bondings that you're supposed to understand. Number one is what we call a polar covalent bond, and number two is what we call a non-polar covalent bond. So it is very important for you to understand these concepts. So when we're talking about polar, we're talking about an equal distribution or an equal sharing of electrons. Others will call it an even distribution of electrons. Then on the other hand, in non-polar covalent, there is equal sharing of electrons. So what you should understand here is that in polar covalent bonding, there is what is called the aspect of electronegativity. Now in this case, we're talking about the change in the electronegativity. For polar covalent, it is greater than or equal to 0.5. On the other hand, for non-polar ones, the change in electronegativity, it is going to be less than 0.5. So these figures are very, very much important for us to understand if we're going to understand this topic. So because of the unequal distribution in electrons, let me say this is carbon and this is oxygen. So oxygen is going to pull electrons towards itself. So because of that, you're going to have what we call a dipole, and the way you present a dipole is an arrow and you represent it like that. This shows that this molecule, or this compound, is polar. It has two poles. Now a partial positive and a partial negative. Okay, and this is very important for us to understand. On the other hand, non-polar molecules, let me say examples like a carbon and a hydrogen, because their electronegativity is less than 0.5, so you find that the dipoles just tend to cancel out each other. Okay, so in most of molecules like oxygen, hydrogen atoms like that, most diatomic molecules also are non-polar, and this is very important for us to understand. So that is some of the things that you're supposed to understand. Then in this session we're also going to talk about what we call Lewis structures. So a Lewis structure will just be a very simple diagrammatic presentation of the bonds that are reacting in the chemical reaction. Mostly are focusing on the valence one, the one with valence electrons, the outermost shell. Okay, an example, if I've got hydrogen and hydrogen, this is, let's say, H2. So this one is going to share its electron in its outermost shell. This other one will also share its outermost electron in its shell. So how are you going to write in terms of Lewis structure? You're going to say, you just put like this and like that. The middle here just shows that there are 2 electrons there. Each one of them is sharing an electron, and that is very important for us to understand. Another example that we can give here is if I've got, let me say, chlorine and let's say another chlorine molecule. Okay, another chlorine atom. So you know that chlorine has got about 7 valence electrons, so you're going to put your electrons in. So these are 6. So this one is the first one is going to contribute 1, and the other one is also going to contribute another one. At the end of the day, what will be your final structure or your Lewis structure? So it's going to be C. Now you're going to put a dash. Now a dash presents, like we've said, it's a bond that has been formed now, the aspect of now chemical bonding. So this will be like your Lewis structure. Now sometimes what you're seeing there, other atoms are not involved in the reaction, like these atoms. The atoms that are being just involved in the reaction are these atoms on the middle. So those are what we call lone pairs. Now how do we find lone pairs? You're going to find your lone pairs by the group number minus the electrons that are shared in the in the reaction divided by 2. This is another formula that I don't want you to forget. That is very, very important for you to know. Then you also have to understand what we call dipoles. Now di means 2, poles meaning this molecule has it has 2 poles. But now dipoles, the way they come about, some molecules are not going to have a dipole. For example, let me say carbon dioxide. Okay, so I'm going to have my C, and I'm also going to have my oxygen this side, and I'm also going to have my oxygen the other side. So now what are we talking about? Because oxygen is more electronegative than the carbon, this one is going to pull electrons from the carbon. This one is also going to pull electrons towards itself from the carbon. So because both of them are pulling in opposite direction, and according to your vectors, what's going to be a result? You're just going to have because this one is going to be partial negative, this one is going to be partial negative as well. But now we are going to have 2 partial positives on the hydrogen. Okay, therefore everything balances, and therefore there will be no net dipole, and there is no no charge. So this compound is non-polar, it doesn't have a pole. Then those molecules with maybe a dipole, let me say they are polar, for example like water. So you know that this is your oxygen, let's say it's reacting with our hydrogen there and another hydrogen. The bonds are formed like that. Now oxygen is pulling electrons towards itself, so I'm going to draw a dipole this side. Oxygen is pulling electrons towards itself, I'm also going to draw a dipole on the other side. So now what are we going to result as? Now you understand that if this is a dipole, look at the direction in which they are going. In this case they are not in a linear fashion. So if we're going to do from our concept of vectors, we're going to get the y component, and let's say the x component for this one. Let's say this is the y, this is the x, and this other one we're going to get also the y component and the x component. Okay, now the fact that these vectors are going in the same direction, what are we going to do? You find that they are going to cancel out each other in the x direction. But what about the ones in the y? Look at, they are going in this direction and the other one is going in that direction. So because they are going in those directions, they are going to add up. Okay, therefore at the end of the day, you're going to have oxygen with a partial, two partial negative charges like that, and that is very important for us to understand. Then lastly on this topic, you're supposed to understand what we call formal charge, the charge of each of the individual atoms in the, let me say, in the bond that has been formed, okay, or in the chemical reaction, or in the chemical bond itself. So it's going to be found by the valence electrons referring to those electrons in the outermost shell, minus the ones that are involved in bonding, plus the ones that are not involved in bonding or non-bonding. So this is the formula that we are going to use for formal charge. Now that we've talked about some of the basic concepts, let's now solve our questions. So the first question we're asked is, what is a dipole? Now a dipole, we're just talking about the separation of charge, like we says it occurs when there's a difference in electronegativity between those atoms that are bonded. Okay, so you are going to realize that the larger the dipole moment, the more polar the molecule is, and that's about a dipole. So it is very, very important for us to understand the dipole like that. Then number 2, we're told to arrange the following bonds in the order of increasing polarity. Okay, so we've got C to H, we've got F to H, we've got N to H, and we've got O to H. So what are, in terms of increasing dipoles, that your carbon is just 2.5 in terms of electronegativity, your hydrogen is 2.1. Then your F, your fluorine, in terms of your fluorine, that is F to H. Yes, your fluorine in terms of electronegativity is just 4. Hydrogen is 2.1. What about your nitrogen? Nitrogen is 3. Your hydrogen is 2.1. Oxygen is about 3.5. Nitrogen is 2.1. Now let's find the difference between these ones, so that we see which one is the least polar. Now between carbon and hydrogen, if we are going to find the difference, 2.5 minus 2.1, I'm finding 0.4. Then I come to the second one, 4 minus 2.1, I'm just finding 1.9. okay, then I come to this one, 3 minus 2.1 for N, I'm finding 0.9. Then I come to the last one, 3.5 minus 2.1, what do I get? I get 1.4. So now that I've got these figures, they are going to tell me which one is most polar, which one is the least polar. Okay, so we come to which one is the most polar. Okay, so our 1.9 is going to be the most one. Then which one is going to be the least? Okay, in terms of polarity. So in terms of polarity, we're going to have the one 0.4. So this is 4. This is 1. Then which other one between these ones? This one will be 3. This one will be 2. This one will be 3. Okay. So how are we going to arrange them? So in terms of increasing, we're starting from the smallest one. So we're going to say in terms of we're going to say C to H in terms of increasing. Then we're going to now move to F. We're going to actually not really. We're going to move to the second one, which is N. What are we writing? We're going to move from N to H. Then we move to O to H. Then F to H. So that's how we are going to write our expressions like that. Okay, now that we've got this, so what is number 3? Which of the following pair of atoms, which of the following pairs of atoms are likely to form ionic bonds? B, boron and carbon, calcium and nitrogen, beryllium and fluorine. So let's start with boron and carbon. So are they likely to form, what ionic bonds? Then what have we said about ionic bonds? We said ionic bonds, mostly they are formed between a metal and a non-metal. Now boron and carbon, these ones are non-metals. They are unlikely to form an ionic bond. So I've cancelled those ones. What about calcium and nitrogen? Okay, calcium is a metal, nitrogen is a non-metal, so they are likely to form an ionic bond. So these ones qualify. What about beryllium and fluorine? Okay, so beryllium is a metal, fluorine is a non-metal, so they are also likely to form a what we call an ionic bond. So in this case, calcium and nitrogen, beryllium and fluorine are most likely to form ionic bonds. What about now, let's solve now D. D, we are taught to predict the increasing order of electronegativity from each of the following set of elements. So how do we predict the increasing order of electronegativity from each of the following set of elements? Okay, so electronegativity. So you have to understand that electronegativity, which is the tendency of an electron to pull an atom to pull electrons towards itself. So what I'm supposed to know is that electronegativity generally increases across a period. It increases across a period. Okay, then it decreases down a group. So this is very important on the periodic table. So if we're going to talk about the period increase, they predict the increasing period of increasing order of electronegativity from these atoms. So how are we going to predict? So in terms of increasing order, let's start with increasing order. So what are we going to have? You know that fluorine, it is the most electronegative element. So in this case, if we're talking about increasing electronegativity, fluorine will be like the last one. Actually, most nonmetals themselves, they are more electronegative. So fluorine will be like the last one. Then on this list, which other one can we also pick? Oxygen is also more electronegative. Then which other one? In this case, we're also going to get carbon. Then we are now going to put which other one? We can now put lithium as the last one from the first list. Okay, so this is how we are going across a period. Okay, so just to comment on the electronegativities, fluorine we've said it is 4. Oxygen we said is about 3.5. Carbon we said is 2.5. Now lithium is about 0.98. So these are the figures in terms of electronegativity. So that's how you're going to show for those ones. What about set 2? Now if you look at set 2, those are metals in the same group. So in the same group, we said they increase in terms of electronegativity, they decrease, right? That's what we've said. So we're going to start from the one which is most and coming down to the one that is least, or we can do the opposite. So we have beryllium, chlorine, S, and Se. So actually that's sulfur. Okay, so you know that Te, it has got an electronegativity of 2.1. Se, it has an electronegativity of 2.5. Then sulfur has got an electronegativity of 2.6. Then your chlorine has an electronegativity of 3. So based on this information, you're able to see that we are moving now from, we are going in this direction. We are going in that direction. Okay, so this will be the increasing order, going to the most electronegativity to the most electronegative. Why? Because chlorine is a non-metal, sulfur is a non-metal, but these two are like metals. So as we are going in this direction, we are tending to increase in terms of electronegativity. So that's how we solve the first question. Then number 2, we are asked from the given, from the given molecules, identify the polar and the non-polar ones. Give a reason for your answer. Okay, so how are we going to comment on polarity and our reason? Okay, so if we're going to look at nitrogen is, this nitrogen is connected to 3 chlorine atoms. So I can put chlorine here, I can put chlorine, I can put chlorine. Now nitrogen needs like about, it's got about 5 electrons in its outermost shell. So it means it has a lone pair, it has 2 lone pairs there, or it has a lone pair of electrons on top. So because of that, nitrogen is going to be, it's going to be polar. Okay, so because of that, so nitrogen in this case, it is polar. The reason is that because it has a lone pair, so this makes now nitrogen to have a trigonal pyramidal shape, which now results in an even distribution of charge. Now what about sulfur? Sulfur dioxide. So sulfur dioxide, if this is our oxygen, and in terms of lone pairs, how is our sulfur dioxide going to be? So we know that sulfur dioxide, because of the nature of the way it is, the oxygen atoms themselves, they are going to, oxygen itself is just more electronegative than sulfur. So because of that, it's going to be pulling electrons towards itself. So this is also going to be polar. Okay, reason is because oxygen is more electronegative than the other one, so it pulls electrons towards itself. Okay, and that will result in partial charges. Okay, so this usually is a band structure for sulfur dioxide. Then we have got beryllium dichloride. Okay, now beryllium and chlorine, so this is just a linear structure. So if this is a beryllium, and we've got our chlorine this side and our chlorine that side, so because it is linear, what are we going to have in a linear structure like this one? Chlorine, which is a bit more electronegative than beryllium, pushing electrons towards itself, and also the other side. So because of that, we're just going to have a non-polar molecule. Okay, so in this case, this one was saying it's non-polar. Okay, so the dipoles themselves, they just cancel out. So those are some of the reasons. Then we've got the barium trifluoride. Now it's boron trifluoride. So now what about boron trifluoride? So for boron trifluoride, this one is a bit different. So for it, it's going to have a this is our boron. Boron is one of those atoms that undergoes what do you call this one? it undergoes an expanded is it octet? Yes. So it's able to accommodate a lot of structures. So that is our fluorine, that is our fluorine, that is our fluorine. Now so the bond dipoles are going to cancel out each other, because this one is pulling electrons, this one is also pulling electrons, even this one is also pulling electrons in that direction. All of them, they are going to cancel out each other, and this will be also a non-polar structure. Okay, so that is important for us to understand. Then number two, we're taught to draw the Lewis structures for the following compounds. Now we've talked about how you draw Lewis structures, so I'm just going to go direct to drawing these diagrams. So if the first one is our P there, our phosphorus. So what are we now going to have? We've got three boron molecules, so we've got B and B and B there. So I'm going to put my bromine molecules actually. So even this side, bromine. Now we also have to consider the number of valence electrons and how these electrons are arranged. So valence electrons, those electrons that are in the outermost shell. You know that your phosphorus has got 5 valence electrons. Okay, bromine itself, this is your phosphorus. Bromine itself, how many valence electrons does it have? So bromine has got about 7 valence electrons, but now we've got 3 of them in that case, so we're going to multiply by 3. So what are we going to have? We've got 5, then 7 multiplied by 3, that is just a 21. So we're supposed to add the 5 and a 21, so we're going to have 26 valence electrons. Okay, and that is very important for us to understand. Now that we have that, we just have to now arrange all the atoms. So what are we now going to have? So how many electrons are used? So if we put electrons, this is 1 2 3 4 5 6, 1 2 3 4 5 6, 1 2 3 4 5 6. Okay, so this is like 8, this is like 8, this is also like 8. Okay, that will be like 24 of electrons have been used from 26. So from 26, since 24 have been used, so when we subtract, we're going to have 2. Where are we going to put the 2? So those 2 act as the lone pairs here. So that will be our final structure with lone pairs of electrons on the phosphorus atom, like that. So that's how you solve the first one. Let's solve the other one. So we're solving the sulfur hexafluoride. Now how do we now put these electrons? So you know that the sulfur will be the central atom. You've got your electrons like that. Okay, these are 6, right? Yeah, 6 like that. So this is fluorine, this is fluorine, 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 and another fluorine. So this is the structure that we have. So how do we come up with this structure? We also have to consider the valence electrons, the electrons in the outermost shell. You know that sulfur is in group 6, so it has 6 valence electrons. Okay, fluorine itself, you know that it is in group 7, it has 7 valence electrons. Now because there are 7, it is in group 7 and it has 7 valence electrons. Look at chlorine, we have got 6 of them, so we're going to multiply this 7 times 6. So we're going to have 6, 7 multiplied by 6, that is like a 42. So 6 plus 42, I'm just going to have 48 electrons. So those are the valence electrons that we have. So let's count if we're going to have 48. So we put our electrons. These are 5, these are 6. I also put 6. Okay, so this is 8. This is 8. This is 8. Okay, that is 8, 8, and another 2, 3, 4, 5, 6, 7, 8. Okay, so it balances. So all of them are going to be used up. No lone pair, nothing. So this is how we're going to solve, and that would be the structure for our sulfur silicon. Actually, this is silicon tetra. This is sulfur hexafluoride. Okay, now let's come to see how are we going to solve our silicon tetrachloride. Okay, so also have to consider the valence electrons. Now silicon in terms of valence electrons, silicon is in group 4, so we're talking about 4 valence electrons. What about chlorine? You know that chlorine is just in group 7. So what then how many chlorine atoms do we have? We've got 4, so we're going to multiply it by 4. So we have 4, then 7 multiplied by a 4. What do we have as an answer? 7 multiplied by 4, that is just like 28. So 4 plus 28, that just gives us 32. So we've got 32 valence electrons for these atoms. So now how are we now going to do? So we're going to also again put silicon at the center. Then now we put our electrons. So we've got 4 of them. Let's say this is this one, and that one, and that one. So this is chlorine, this is chlorine, this is chlorine, this is chlorine. Okay, 32. So let's start put 1, 2, 3, 4, 5, 6. So we've used 8. 1, 2, 3, 4, 5, 6. We've used another 8. 1, 2, 3, 4, 5, 6. We've used another 8. Okay, so that is like then if we use another 8, 1, 2, 3, 4, 5, 6, we're going to have 8 like that. So all of them are going to be used up. Okay, so all of them are going to be used up, because if you multiply 8 by 4, it's just going to give you a 32. So all of them are going to be used up, and this is what we are calling in terms of the geometry, the way the shape looks like. This is a tetrahedral shape. Okay, then I think the previous one, for this one we had to see like it had to, this one is saying it's a tetrahedral. This other one, which has 6, the shape looked like it was an 8. This one is called an octahedral. An octahedral shape. Oh, that was the geometry. Now what about the first one? This one we said it is trigonal pyramidal. Okay, so that was very important also for me to mention. So that's how we solve this one. So now we've got number 3 here. We are told the Lewis structures for 3 molecules are given below. Complete the table by giving the name of the shape of each molecule. Okay, so we're just giving the name of each of these molecules. Okay, so they've given us the molecule, they've given us also the structures. So this is even more simpler for us, making the work more simpler for us. So this is, what is the name of this molecule? This is dichloromethane. Okay, now dichloromethane what will be the structure. So first we have to count the regions of electron density. Okay, so carbon, in this case, we're able to see that it is in the center. So since carbon is in the center, it makes 4 bonds. So 2 with chlorine and 2 with hydrogen. You're able to see that 2 with chlorine and 2 with hydrogen, like that. So those are some of the electron density areas. So therefore, what would be the electron geometry? Electron geometry, in this case, what is it going to be? So because it is bonded to 4, there are 4 regions where we're likely to find bonds in this case. So this is going to be a tetrahedral. In terms of electron geometry, so it's going to be tetrahedral. Okay, what about the molecular shape? How does it look? So it also looks, a tetrahedral. So this, now the name of the shape would be tetrahedral. That would be the molecular shape, the way the molecule looks. Then we've got nitrogen trichloride. Okay, now nitrogen trichloride, we're also going to count the number of electron density areas. So you're able to see that this one, it has a lone pair of electrons on top. So even those ones, we count them. Nitrogen makes 3 bonds with chlorine atoms, and it holds 1 lone pair, so giving a total of 4 electron regions of electron density. So there are 4 of them. In terms of electron geometry, there are 4. Okay, so because there are 4, what would be the electron geometry? We're talking about a tetrahedral. Okay, but the molecule itself, okay, the molecular shape, if you look at the molecule, the way it looks like a trigonal pyramidal. It looks like a pyramid, but we have like a lot of pyramids. So in this case, this one is going to be a trigonal pyramidal. Okay, trigonal pyramidal. Okay, so this is a similar structure to NH3 in ammonia. Okay, this is a similar structure. Because of those lone pairs, you tend to have that kind of a structure. Then for those ones who don't know, you can also just check on our YouTube channel. You're going to find videos on chemical bonding. So that is very important for you to also understand. Then the last one, we've got boron trifluoride. So boron trifluoride, we also have to count the regions. Although the shape is not clear, the Lewis dot structure is not very clear, so we also have to count. Boron is just on the middle. So boron, you're able to see that it forms 3 bonds with fluorine atoms, and it has no lone pairs in this case. So what would be the electron geometry? So with 3 bonding regions and no lone pairs, the electron geometry for this one is going to be a trigonal planar. Okay, trigonal planar. This will be the same for the the molecular shape. Okay, so this is how you're going to talk about that. Then question number 4, we are told to, what are we told on number 4? So we are told to draw the Lewis structure of the following molecules that violate the octet rule. So I'm just going to draw the first one on this one. This is xenon. Okay, xenon, we know that it's one of those noble gases. It is a very, very stable atom. Okay, so it's connected to 4 fluorine atoms. So this will be fluorine, this will be fluorine, this will be fluorine, and that will be fluorine. Okay, so the whole molecule in terms of valence electrons, fluorine, like 7. Okay, so this is going to be like 36 valence electrons. So of the 36, how are you going to do that? So let's count. So 1 2 3 4 5 6, 1 2 3 4 5 6, 1 2 3 4 5 6, 1 2 3 4 5 6. Okay, so this is 8, this is 8, this is 8, this is 8. So we're going to have 32. Now 32, we've used 32, so we have to subtract from 36, and when subtract we are going to have 4. So you're able to see that xenon is going to now have two lone pairs. So now this will be the final structure. It has violated the octet rule, okay, because how many electrons is it supposed to be stable? Only 4. To share 4 electrons and to be stable, but it has gained 4 more. So this is a violation of the octet rule. So that is very important for you to know. Now there's another question here about from the molecule below. State the hybridization. State each of the labeled carbon atoms. From the hybridization below. So that is the question that we have in terms of the hybridization. So we have a diagram there. So what are we supposed to do? So from the molecule below, that is the molecule, state the hybridization, state each of the labeled carbon atoms. Okay. So that is the molecule. So what would be the hybridization for H? Okay, or state the hybridization, set each of the labeled carbon. Okay, the labeled carbon atoms, there is A, there is B, and there is C. So what would be the hybridization for carbon? Now able to say that carbon here is bonded to 1 and here is also bonded to 1. It has 2 electron density areas. So in that regard, what are you going to have as the hybridization? So you're just going to have, this one is going to be sp. Okay, then what about B? B is also going to be sp because they have 2 electrons, this one and this one. Okay, now what about the last one, C? Now the way C is, it is like this. It has H3. H3 to mean if I'll put a hydrogen here, I'll put a hydrogen there, I also put a hydrogen there. Now it's connected to how many electron density areas do you have? You've got 1, 2, 3, 4. Because of 4, what are you going to have? You're going to have sp3 hybridization. So this will be sp3 hybridization, and that's how you are going to go about this one. Then be told how many sigma and pi bonds are there. So now you know that in every single bond there is a sigma bond, but in a double bond, in a triple bond, in a double bond you're going to have 1 pi bond and 1 sigma bond. So what are you supposed to know? So if we're going to count the number of sigma bonds, let's start with sigma bonds, and you also have to count the pi bonds. Okay, so sigma bonds, we have one from H, let's say H to A, this is 1. A to B, this is 1 as well. Then when we come to B to C, we also have 1. So what about C to H? We've got about, because you remember we had like C like that, it's connected. So how many are we going to have? We're going to have this one, this one, this one. So we have 3 here. those are the sigma bonds that we have. So we have 1 plus 1 plus 1 plus 3. That will just give us 6 sigma bonds. Okay, so those are the sigma bonds. What about the pi bonds? So because you don't find pi bonds in single bonds, so in this case your pi bonds are only going to be in the triple bond. Now one double bond only has one pi bond, but when you have a triple bond, it means you have 2 pi bonds. So in this case we are saying 2 pi bonds. So this is how you solve this question. Then we are coming to this other question. As we are summarizing, group the following as linear and non-linear molecules. Okay, so we are grouping those ones as linear and non-linear molecules. So we have to use the VSEPR theory, okay, or VSEPR geometry to explain this question. Water, is it a linear structure or a non-linear structure? You know that water gives a bent structure, right? You know that it gives that bent structure. Now, is it going to be linear or not? So you know that this won't be a linear structure because it's bent. What about if we come to the second one? HCl, that's hypochlorous acid. Now hypochlorous acid, because of the oxygen, you know that oxygen tends to push to get electrons towards itself. So this will be H, this will be chlorine. So it's going to be pulling electrons towards itself. Therefore, we are also going to have a bent structure. So in this case, this one will also be non-linear. Okay. What about BeCl2? Beryllium chloride. Now, beryllium chloride, like we solved earlier, so you're going to have your chlorine like that. So because of this, you've got your dipoles going in this side and another one going in that side. Okay, the partial charges going that, so that they're going to cancel out each other and they're just in a straight line. So because of this, and look at the angle from here to there, it is just 180. So this one is a linear structure. So beryllium will be a linear structure. What about what is this? Is dichlorine monoxide. Now what about dichlorine monoxide? So because of oxygen, so you're also going to have a bent structure because oxygen is pulling more electrons towards itself than the other one. And the other thing is that maybe also some lone pairs, 2 lone pairs for the oxygen there, okay, for it to be balanced like that. So that is very important for us to understand if we're going to talk about those ones. Then let's talk about number 10. Now, what is the hybridization and geometry of the central atom in beryllium? That's trifluoride. Okay, so what we're asked, what is the hybridization and geometry of the central atom in beryllium? That is trifluoride. So what is it going to be? What is the hybridization and geometry? So let's start with the structure for this one. So we're talking about beryllium connected to, let's say, actually it's boron. Hey, I'm missing things. So boron. So this is our boron, and it is the central atom. So boron itself has 3 valence electrons, which uses up 3 sigma bonds with the about 3 fluorine atoms. So in this case it doesn't have any lone pairs. So because it's connected to three, there are three electron domains in this case. What would be our hybridization? It's just going to be sp2, actually sp2 hybridization. What about the geometry in itself? What will be the geometry? So this one is going to be, because it's going to sit like in a plane like this, so this is a trigonal planar. Okay, so if you don't understand how this molecules come about, you can watch our videos and you understand. Then, although both carbon dioxide and water are triatomic molecules, the shape of water molecule is bent while that of carbon dioxide is linear. Okay, explain this on the basis of dipole moment. Now, I think we've talked about this when I was just introducing the topic. Water itself, if you are going to look at water, or let's start with the same carbon dioxide. We said carbon dioxide itself is a linear molecule. If this is your carbon and this is your oxygen, like that. So oxygen is going to be pulling electrons towards itself. So because they are pulling electrons at the same force in different direction, the dipoles are going to cancel out each other. So the net dipole moment of this one is 0. So it's 0. Okay, so we are not going to have a bent structure in this case. But when you look at water itself, we said this is your oxygen, these are your hydrogens. Oxygen is pulling electrons in this side towards itself, so the dipole will be going in that direction. But now if you are going to do your vectors, there'll be if you are going to do the components for this dipole, x and y, and you come to the other dipole, the y component and the x component. So these ones, because they are going this direction, they are going to cancel out each other. But these ones, the fact that they are going up, they are going to add up. Okay, so because they are parallel to each other, they are going to add up, and that is the bent structure. Then the other thing is the lone pairs that are there on the on the oxygen. So they are pushing, the lone pairs push the bonded pairs closer together, and this usually create a bond angle. You know that the bond angle that is usually formed is about 104.5 degrees according to your biology. So this is how we solve these questions. So this is what we're going to end for today. If there are any other questions, you can still reach out to us, and you can also access some of the videos on chemical bonding as you are preparing for your quizzes. So this is how we're going to end from today. Thank you and good night.